Hello, so this is the second meeting on the Chapter 7 review, and we will finish part 1. We have only one question to answer at the very end here. It's, question 5, where we need to write the product of the reaction and tell if it is a precipitation reaction or if no reaction happens. We need to write the complete ionic equation and the net ionic equation, if we have a reaction. And we have this last example of sodium nitrate solution and strontium acetate solution mixed together. So we want to find the reactant formula first. So sodium we know is Na+. I think by now you know that it's a positive 1 ion. It's alkali metal from group 1A. Nitrate, and so nitrate, let me see, I need to find my, nitrate is part of the polyatomic ion list. What tells you it's a polyatomic ion? It's the ending in 8. And here you can see nitrate, where is it? Nitrate here. Okay, NO3 -1. So the 3 is a subscript, so be very careful. It means 3 oxygen bonded to 1 nitrogen, and then there is only 1 negative charge. So together, that's going to be the NaNO3, because you can see that it's, so that's a subscript, not a superscript. So 1 positive charge will cancel the 1 negative charge, and that's the formula for NaNO3, sodium nitrate. You're told it's a solution, that means it's aqueous. And then we add strontium acetate. So let's look at the periodic table for strontium. Strontium here is in group 2A. It's an alkali earth metal, right? So from group 2A, which means it's a predictable ion that is a 2+ ion. So let's write strontium. It's Sr with 2 positive charges. And then acetate. Again, the ending in 8 tells you it's a polyatomic ion. So here, acetate, where is acetate? Sorry, oh, yes, now I see it. Here, acetate. Okay, C2H3O2 -1. So C2H3O2 and 1 negative charge. So all of this is not a superscript. So the 2 here is a subscript for carbon. You have 2 carbon, 3 hydrogens, 2 oxygens, and 1 negative charge only. So here we will need to do the crisscross trick to find the formula of that, because we don't have the same amount of charges on both sides. So it's going to be Sr, and then again C2H3O2. And the negative charge here on the acetate means it's going to be a subscript of 1 for strontium, so no subscript for strontium. And then the positive 2 charge here means you will have a subscript of 2 for the acetate. So we need parentheses around the acetate to show that there is more than 1. And then we said we need 2 acetate, and that should be a subscript. It applies to anything that is in the parentheses, so that tells you you have 2 acetate per strontium. And that's again an aqueous solution, so AQ. Then we need to find the formulas of the reactant, of the product. These 2 are the reactant. We need to find the product. And again, this is a reaction where you have aqueous solution, which means you have these ions floating around in the water, right? And they are free from each other. And so they can mingle with the other ions. And so, for example, the Na plus can mingle now with the other negative ion, and the other negative ion is the acetate. So instead of being with the nitrate, sodium can go with the acetate. And so because you see that you have one positive charge, one negative charge, so one of each ion will make this a neutral formula. So then we know the formula will be just Na and then C2H3O2. So you keep Na in front because that's the positive ion. Now we need to find the solubility of that sodium acetate. So for this, you need to move to the solubility rule table. And we need to find the acetate or the sodium, right? And we have sodium here or the acetate here. They are both among the compounds that are mostly soluble, and there is no exceptions for both. So that means definitely a soluble compound here. Soluble compound means you will write AQ. It's aqueous and it's ions free floating in the water. Now we need to add the other product. And the other product will be made from the combination of the other positive ion, so strontium, mingling with the other negative ion, so the nitrate. Instead of being with the acetate, it can go with the nitrate. So here we will need the to use the crisscross trick, and we can see that the one negative charge of the nitrate will make it a subscript of 1 for strontium. And then the 2 from the charge of the strontium means you will need 2 nitrate. So if we need 2 nitrate, then we need parentheses around the nitrate because we have more than 1. And then outside the parentheses, the 2 indicates 2 nitrates. So again, we need to find the solubility of this compound, strontium nitrate. And here, strontium nitrate. The nitrate is here. Again, among the sodium and the acetate, and there is no exception, it makes soluble compound. So that means strontium with the nitrate will be also an aqueous solution, and you know the ions will be free floating in the water. So let's balance this. We have 1 sodium on the left, 1 sodium on the right. And strontium, same, 1 strontium on the left, 1 on the right. What we need to balance are the polyatomic ions. And you have 2 acetate on the left, but only 1 on the right. So that means we need the 2 in front of the Na C2H3O2 to make it 2 acetate. And then we need also to balance the nitrate. And the nitrate, we have 2 nitrates on the right, only 1 on the left. So let's make it 2 nitrate by having a coefficient of 2 in front of NaNO3, because we want to have 2 nitrates. And this will help balance the sodium, because you saw that with the coefficient of 2 in front of NaC2H3O2, we have now 2 sodium on the right, but this will make it also 2 sodium on the left. So let's make sure it's balanced. So 2 sodium on the left, 2 sodium on the right. 2 nitrate on the left, 2 nitrate on the right. Still 1 strontium on the left, 1 strontium on the right, 2 acetate on the left, and 2 acetate on the right. So it is balanced. And the question was, do we have a precipitation reaction or is there no reaction? And here, the sign for a precipitation reaction, and then we can look at this document here. Remember, that's documents you can find on Canvas in the chapter 7 module. To recognize a precipitation reaction, you want to find that one of the product is insoluble, and you have to start with soluble ionic solutions mixed together. So from two solutions, do we get a solid? No, we didn't, because we have only a soluble compound, soluble product. So this is not a precipitation reaction. So that means we can say here, this is not a precipitation reaction because all products are soluble. No precipitate was made. So you can visualize this as a mixture. It is a mixture of ions in water. And I should say free floating ions, of free floating ions. They are really free from each other, only surrounded by water. So it's not a precipitation reaction. And then, because it's not a precipitation reaction, there is no point of writing the, net ionic equation, or the net ionic equation would be the same as the complete ionic equation, right? And yeah, we could write the complete ionic equation, and it would just show all these ions balanced. And that's it. And then the net ionic equation would stay the same, because there is no, well, actually it would stay the same, or there would be nothing, because there is no reaction. So it's just a mixture of free floating ions. They don't mingle together. So there is no point of doing those ionic equations when you have no reaction. Let me correct this precipitate. So we will continue with the chapter 7 review, part 2. It's more about reaction types. And so we have seen up to now only precipitation reactions, or just mixture of ions from no reactions from two aqueous solutions. Here we will dwell into acid-base reactions. And so we need to find the product of the following acid-base reaction. So you are told it's an acid-base reaction. And once you have the balanced molecular equation, you will need to write the complete ionic equation and the net ionic equation. So let's start with 1A here. So the acid is the compound that has H, the hydrogen, as first in the formula. So the acid is HNO3 because it has H as first in the formula. And then the base, it's a strong base, and we recognize strong bases because they have the OH minus ion in their formula, which is the hydroxide ion, right? The OH minus ion. OH minus ion. Let me, yeah. OH minus ion is the hydroxide ion, and that's what makes this a strong base. The Rb is rubidium. So let's find Rb in the periodic table here. Rb is just next to strontium. It's in group 1A, so it's a +1 ion, rubidium. And it makes sense here because it's with with only one hydroxide. So Rb is Rb+. So we have these two ions. And yeah. And then from the acid, so an acid, what's particular about an acid is that when you place them in water, when they are, aqueous solutions, they are made of the H+ ion and the NO3 nitrate here in this case. So let me format that properly. Again, nitrate is made of 1 nitrogen and 3 oxygen. And then the H+ ion is just from hydrogen. So this means that you have that in solution, right? All these ions floating in solution, because these are aqueous solutions. And so when you have free floating ions, they can combine with other partners. For example, the rubidium can decide to partner up with the other negative ion and other than the hydroxide. So it can go with the nitrate instead of the hydroxide. And so we need to find the product formulas by doing this new combination. And so when rubidium combines with the nitrate, we have RbNO3. And one of each ion makes this a neutral formula. So it's just one Rb for one NO3. So this is the one of the products formula that we can make. And so let's find out its solubility. You go to your solubility rule table, and here, so the nitrate is here again, and it says no exceptions. It's always making soluble compounds. So we know that this is going to be aqueous then. It's a soluble compound. So let's find the other possible product out of this mixture. So the other positive ion, H+, can decide to combine with the other negative ion, and that's the OH- here, instead of the nitrate, you know. So when H+ combines with OH-, so if you look at this carefully, the formula will be H2O. And that's water, right? So when you are mixing an acid with a strong base, you're forming water. And the physical state for water in this case is liquid, because water cannot be aqueous, right? Water is the solvent already in there. And so you're forming just more water, and it's going to be in the liquid state. So the state for water is liquid. And from the beginning of the chapter 7 that the formation of water is a driving force for reactions. And so for acid-base reaction, the driving force is the formation of water. And so the general form of an acid-base reaction is that the acid plus the base are forming water plus a salt. That's the general form of an acid-base reaction when the base is a strong base. Let me specify that. This is the general form of an acid-base reaction when an acid reacts with a strong base. It only is very true for strong bases. A strong base is made of the hydroxide ion and then a metal, like rubidium OH- here. So you can see that it is already balanced. So if we look at the polyatomic ions, we have OH- here, and we retrieve OH- in the water. And then water is made of the OH- plus the H+. So one of OH- and H+ will make one molecule of water. So that's balanced. And we still have one rubidium, and then one nitrate. So this is balanced. So this is what we call our balanced molecular equation. So we are asked to write the complete ionic equation and then the net ionic equation. So let's write the complete ionic equation first. So complete ionic equation of this. So I already gave the ions there, right? So I can actually start using that. And because we have water here, and whenever you are forming water, we just said that it's a driving force, and water will be the water molecule. It will not be the ions. So this will stay as water on the right side. But the rest, everything is soluble. And so everything will be in the form of the ion. So I can copy that and rewrite this. And we have the arrow here in between. So we will write AQ for each of the ions, because here they are free floating, and then the physical state for each of these ions is aqueous, because they are surrounded by molecules of water and free floating. So I've added the physical state of aqueous for each of the ions. So we have the rubidium plus, the hydroxide minus, H plus, the nitrate minus. That's on the reactant side. And then on the product side, we have the rubidium again, and then the nitrate, and they form this compound here that is soluble in water. And then the only thing we are missing here is the water. These H plus and OH minus, when they form water, they are forming water. You cannot keep them as ions. Formation of water is the driving force for acid-base reaction. So this is the complete ionic equation here. And then it's balanced because there is one of each ion on both sides. So now let's write the net ionic equation. So remember, to write the net ionic equation, you keep your complete ionic equation, and you're removing the spectator ions, right? We remove spectator ions. And spectator ions are those ions that are present on the reactant side and on the product side, and they don't participate into the reaction. They are just floating around and not doing anything special. So we can see here on the right side, we have rubidium, and on the left side, we have rubidium. So we can remove rubidium. It's the same on both sides. Nitrate, we have nitrate on the right and nitrate on the left. Same, so we remove them. And that's it. The rest is not the same, right? On the left side, we have H plus plus OH minus, and then on the right, it's H2O. And so this is typical, this is typical of the net ionic equation. Oh, this is, hold on. So this is the net ionic equation that you will always get for an acid-base reaction when you have an acid reacting with a strong base. It will always come down to the H plus coming from the acid, reacting with the OH minus coming from the strong base, and making water together. So that's why the driving force of an acid-base reaction, when you have a strong base, is the formation of water. It's the driving force. Because water is a very stable molecule, very low energy, and the compounds will always favor the formation of water. So that's why it's a driving force. It makes those reactions happen. So I did those lines here to show how, the positive ion from the first reactant will go with the negative ion of the second reactant. And then the negative ion of the first reactant will go with the positive ion of the second reactant. So there is an exchange of partners, when you have acid-base reaction. So following that principle, we can do the same for the next example here. So the first thing to do is to find the formulas of the ions. So again, these are aqueous solutions, which means you have free floating ions in water. So in HClO4, so first of all, this is the acid because it has the H as first in the formula. And here you have the OH minus. Notice how you have the hydroxide ion. So that's going to be the base. So Na plus and OH minus. But here, what are the ions in there? So we know we have H plus. But what is the other one? It's a ClO4. And if you look at the list of polyatomic ions, so let's find this. Oops, here. If you look at the list of polyatomic ions, where is ClO4? Is just above the acetate. ClO4 is here, and that's called the perchlorate. And it's one negative charge, which is confirmed by the fact that it's with one positive charge from the H plus. So ClO4, one negative charge. So again, the charges are superscript. And it's only one negative charge. Be careful, the 4 is a subscript. It's very important to not get those mixed. So that's the ions from the acid. And then from the base, we have Na plus, we recognize Na plus, and then we set the hydroxide ion OH minus. So Na plus and OH minus. So that's our mixture of ions. And just like we did above, we can do an exchange of partners between the positive and negative ions. So that means the H here will go with the OH minus, and then the Cl minus will go with the Na plus. So let's write the formulas that comes from this exchange. So we have, let's do H plus first with OH minus. And we already know what this is, right? H plus with OH minus is H2O, right? We can copy that from here. So it is H2O. You see how you have two H, one O. And that's water. And water is a liquid in this case, because that's the solvent of these aqueous solutions. So it's a liquid. So you're just making more of water. And that's why these reactions are called neutralization reactions, because, from an acid plus a base, you make, and remember here, from an acid plus a base, you make water plus a salt. And water is neutral compared to the acid and the base. So that's why we also call those reactions neutralization reaction. Let me write this here so you understand. Neutralization reaction. Right? Because you're neutralizing the acid and the base, which are opposite properties. Okay, and the other combination is from the Na plus, Na plus, combining with the negative ion of the other compound, and that's ClO4 negative 1. So you can see one negative charge on the perchlorate, one positive charge on the sodium. That means together they will make a neutral compound by having just one of each ion. So you can write them next to each other and remove the charges. So now we need to decide, is this soluble or not? So let's find the solubility rule table. And we have the sodium with the perchlorate. So perchlorate is not here, but we do have the sodium. Sodium is there. And there is no exception. Sodium makes only soluble compound. So that means this is going to be aqueous, soluble in water. So aqueous. Next, we want to balance this. So let's see. We have 1 H plus with 1 OH minus, making 1 molecule of water. So that's good, it's balanced. Then we have the perchlorate here and perchlorate there on the right. And then 1 sodium on the left, 1 sodium on the right. So again, it is already balanced, just simply by having the formulas like that. So that's our balanced molecular equation here. And again, it follows the form of acid plus base make water plus a salt. Because any kind of ionic compound that is soluble in water is called a salt. Yeah, maybe I should type this. Any ionic compound that is soluble in water is called a salt. Even those that are insoluble, I think, are called a salt, but it usually is more said for the ones that are soluble in water. Right, it has to be ionic, not molecular. So any ionic compound that is soluble in water is called a salt. So the next step is to find the complete ionic equation. So let's do that. Complete ionic equation here. Again, we already have our mixture of ions written down here. So I will copy that and keep them here. That's what we have on the left side. Then on the right, we have water. Remember how water stays the same. It's not a mixture of ions, it's the molecule of water that is made here. So you have to keep it as water. You cannot make it ions. But this NaClO4 is going to be ions floating in water. So this will be ions. So let me add the fact that all of these are aqueous. So it's the formula of the ions, but they are each aqueous, right? So H plus aqueous plus the perchlorate is another aqueous ion plus the sodium. And then the hydroxide ion are making water plus the sodium ion and then the perchlorate ion. Right? And because it was balanced without any coefficient, all coefficients are ones. So this, again is balanced, right? The H plus the OH minus are making the water. Na plus and ClO4 minus, you retrieve them on that side. So that's the complete ionic equation for this. And now let's write the net ionic equation. Again, we remove the spectator ions from the complete ionic equation to find the net ionic equation. So we can rewrite this. And then I'm lucky I can erase, but on paper you need to rewrite. So let's remove what's the same on both sides of the arrow. So here we have the perchlorate, and it's the same as here, the perchlorate ion. So we can remove that. And then we have the sodium ion, and it's the same here, the sodium ion. And once you have removed that, you can see that now it's different. On the right side, you have the molecule of water. And on the left, you have the hydroxide ion and the H plus ion combining to make the molecule of water. And again, you see how it is exactly the same as what we had above, because this is the net ionic equation for an acid-base reaction. When you have a strong base, it's always going to be of this form. So you can expect that if you have an acid-base reaction and the base is a strong base with an, the OH minus ion in there, in its formula, then the net ionic equation will always be of this form. So in the documents you have, in the chapter 7 module that is titled Types of Reactions, Gas Evolution Reactions. here it shows how the acid-base reactions are of the form acid plus base gives a salt, which is an ionic compound, plus water. And by the way, the salt, yeah, maybe what I said earlier can be confusing, because the salt can be soluble or insoluble. There are acid-base reactions where the salt will not be soluble. So that means we call them a salt even if they are insoluble. And now we will move on to gas evolution reactions. And again, it's a mixture of ionic solutions that are, soluble, ionic compounds in water. But what characterizes those gas evolution reactions is that one of the products is a gas. And there is this slide here that gives you the details of all the gas that are typically formed in gas evolution reactions. There could be the H2S, the CO2, the SO2, or the ammonia. So we'll go through examples of that. So what are the products? So question 2, what are the products of the following gas evolution reaction? Complete the molecular equation and balance them. So let's focus on this one. HBr aqueous plus Li HCO3 aqueous. So that's 2 aqueous solutions. So it fits the pattern, for a gas evolution reaction. So again, because these are aqueous solutions, means that you have ions, free floating in there. And HBr is an acid, right? Because we have H as first in the formula. So the ion will be the H plus ion. And then Br is the bromide, and that's an halogen. Halogens are from group 7A, and they make one negative charge. They have one negative charge, which fits this formula, right? One positive charge, one negative charge cancel. So that's from this HBr, the hydrobromic acid. And then from LiHCO3, we recognize the Li plus ion. Li is one of an alkali metal from group 1A, and so it's going to be a +1 ion. So what is HCO3? So let's look at the list of polyatomic ion, because that's a polyatomic ion. HCO3 is the hydrogen carbonate. It's here. Hydrogen carbonate, or also called bicarbonate ion, right? So HCO3 -1. With one negative charge. So the one negative charge is a superscript. So that's the other ion in this ionic compound. So we have this mixture of ions, and now we will make them exchange partners, because remember, they are free floating, so they can mingle with a different ion. And so the H plus here will mingle with the negative ion there, and then the Br minus will mingle with the Li plus, right? You want to always put the positive ion with the other negative ion. So what do they make together? So let's start with the H plus. When it mingles with the HC2CO3 -1, the bicarbonate. So you see you have one positive charge, one negative charge. So together they will make a neutral formula. So the formula looks like it can be this, but with another H. Oops. With another H in front. Right? Which means it's 2 H's there in front, and the charge disappears. So then we write only one H, and then we put the subscript of 2. And you recognize this as the, or maybe you don't recognize, but it would be good to recognize this as the carbonic acid. H2CO3, that's the carbonic acid. Because it has H first in the formula, it's an acid, right? You saw how I name it, the carbonic acid. And acids are always aqueous. There is no other way for acids. They are always aqueous. So that's going to be an AQ physical state here. And then the other combination of ion is from Li plus and Br minus. So again, one positive charge, one negative charge. So one of each will make this a neutral formula. So we can write just that LiBr. It's a neutral formula. And if we look at the solubility rule for this one, LiBr, if we look at the left side here, we see Li is part of the compound that are mostly soluble, and there is no exception. So LiBr will be soluble. So that means the physical state will be aqueous. So we have these, and let's say it's balanced, right? You can see you have one Li on the left, one Li on the right, one bromine, one bromine. And then the HCO3 combines with the H to make H2CO3. So one thing you need to know is that H2CO3, the carbonic acid, let me write the name here, is unstable. It is unstable, and it will not stay as the carbonic acid in solution. Instead, it will decompose and decomposes into H2O and CO2. So H2O is water, of course, and then CO2 is the carbon dioxide. And sorry, this is a, yeah, H2O. And H2O will be a liquid, right? Because we are in aqueous solution, so that's the solvent, so it's going to be a liquid. However, CO2, the carbon dioxide is a gas at room temperature. So this is going to be a gas. And you see that for one molecule of H2CO3, you will make only one molecule of water and then one molecule of CO2. You retrieve the number of H's, 2, C, 1, and then 3 oxygens. So let's rewrite this equation because it's actually not staying like that because it is unstable. So let's rewrite it below here. And we don't need the A there. Oh, so we have this, but instead we will change this H2CO3 into water. So let me write water there, plus CO2. And water is a liquid, and CO2 is a gas, and that's CO2, right? So instead of H2CO3, now we have water plus the CO2 gas, because this is unstable. And so now you can see why this is a gas evolution reaction, right? Gas evolution, a gas is evolving out of the, the beaker where you mix those two solutions, and you will see bubbles forming in the solution, and then the gas will escape, right? The CO2 gas will escape. So that's why it's called a gas evolution reaction. And we said this was balanced, so this is balanced too, right? We were asked to balance them. So notice how this is, one of the examples there of typical gas evolution reactions that you will encounter. When you have the carbonates or bicarbonates, and here we had an example of a bicarbonate, mixing with an acid. So mixing with any kind of acid. Together, they will form the carbonic acid, H2CO3, which is unstable and which will give the H2O plus the CO2 gas. So that's an example of that. So let's look at the second example. Okay, let's move on to B here. We have NH4 2 times SO4. So this is the ammonium sulfate because we recognize the ammonium NH4 plus and the sulfate SO4 negative 2 plus KOH. KOH is a base, a strong base, because we recognize the hydroxide ion there. So let's break down those two compounds into ions, because again, these are aqueous solutions, which means it's a mixture of ions. So we said we recognize the NH4 plus ion there. So that's NH4 plus. And we need the charge. The charge is just one positive charge for the ammonium. And then we have the SO4 here, right? SO4 is the sulfate. And the sulfate has two negative charges. So those two negative charges are in a superscript. So to not confuse here, the 4 applies to the oxygen. It means you have 4 oxygens surrounding the sulfur. And overall, this SO4 has two negative charges. So that's the two ions from this first reactant. Then the second reactant has the K. K is an alkali metal from group 1A, so that's K plus. And then we recognize the OH minus here, which is the hydroxide ion with one negative charge. So it's important to recognize the hydroxide ion, and you know, those are polyatomic ions that you were asked to remember. So we have this mixture of ions, which means the ions can exchange partners instead of mingling with, you know, the ammonium with the sulfate. You know, the ammonium can decide to go with the hydroxide, the other negative ion in there. And then the sulfate can decide to go with the potassium, the other positive ion there. So that means we can have these new products by, you know, doing these new combinations. So ammonium with OH minus, the hydroxide. And you can see here one positive charge, one negative charge. So this is going to be a neutral formula when you have one of each ion. So you can just remove the charges and write them next to each other. Or else the positive ion first, right? Positive ion first, negative ion second. You do not want to combine the H's together because then it would be unrecognizable. We'd never do that. We keep them when we have polyatomic ions. We keep them, you know, like that, so that we recognize them. Let's look at the solubility rules to decide if this is soluble or not. So we said we have, what do we have? Sorry, forgot what we have. NH4 plus and OH minus. NH4 plus here, NH4 plus is there and OH minus is there, but NH4 plus is enough here to see that there is no exceptions when you have the ammonium. All the compounds that ammonium makes are soluble, no exceptions. So that's going to be soluble. And so that means you type AQ here. Then we will make the other product from the potassium mingling with the sulfate. So here we will use the crisscross trick, right? We see that we have 2 negative charges there, but only 1 positive charge there. So the 2 of the sulfate charge will become a subscript for potassium. So let me rewrite this here above. So we will have a 2 here as a subscript, subscript, to say that we need 2 potassium ions for 1 sulfate, because you know the plus from the potassium here tells you will have only 1 sulfate. So that's K2SO4. Let's find out if it's soluble or not. So K plus or SO4. Here we have K plus. Again, makes soluble compound, no exceptions. So that means it's soluble. You don't even need to look at the sulfate there, which confirms that it's soluble also. So this is soluble, which means the physical state will be AQ. So now let's look at the balancing. So we'll do it roughly like that, because we have polyatomic ion. When we balance equations with polyatomic ion, you keep the polyatomic ion and you count them as one unit. Here we have 2 ammonium, right? 2 ammonium. But here we have only 1 ammonium. So let's make it 2 by having a 2 in front of ammonium hydroxide. Sulfate, we have 1 sulfate on the left, 1 sulfate on the right. Hydroxide, we have 2 hydroxide now on the right, because we have the 2 here in front of the ammonium hydroxide. That makes it 2 hydroxide. So to balance the hydroxide, we need a 2 here in front of KOH. So let's make a 2 here in front of KOH. And now that will balance the potassium, because now we have 2 potassium on the left and we have 2 potassium on the right. So this is balanced. Let's make sure 2 ammonium on the left, 2 ammonium on the right. 1 sulfate, 1 sulfate, 2 potassium on the right, 2 potassium on the left, and then 2 hydroxide on the left, 2 hydroxide on the right. So this is balanced. Okay, it is balanced, but one thing you need to know about ammonium hydroxide, which is an aqueous compound here, the same way that this was unstable, ammonium hydroxide is the same. It's not stable. And I can write here that this ammonium hydroxide is unstable and decomposes as well into, so it's going to be different here, into, it's going to be NH3, the ammonia. And the ammonia is a gas. This is something you will have to learn, because, so ammonia is a gas. And then the other compound will be the water again, which will be a liquid here, because we are starting with an aqueous solution. So ammonia is NH3, that's a gas, and then water. You look at the formulas, you have 1N. The 4 hydrogens plus 1, that's 5 hydrogens. And here, if you count, you have 3 hydrogens in the ammonia, 2 hydrogens in the water, that's 5. And then 1 oxygen in the water. So 1 ammonium hydroxide will make 1 molecule of ammonia and 1 molecule of water. So then we need to rewrite this, taking into account that it's not stable, and what you get is not this after a while. You're developing a gas, and this is changing into ammonia plus water. So let's put the O on this side and have a 2 there. And water is a liquid. So we make water, and then ammonia. And ammonia is a gas, which is the reason why this is a gas evolution reaction again, right? Because we are making a gas. So let's pay attention to the coefficient of 2 that was in front of the ammonium hydroxide. If we have 2 ammonium hydroxide, then we will make 2 ammonia, and we will also make 2 molecules of water. We need also 2 molecules of water there. Because remember how we said for each ammonium hydroxide molecule, you're making 1 ammonia, 1 water. So if you have 2 ammonium hydroxide, you will make 2 molecules of water and 2 ammonia. And so that's actually the final version of this equation. It shows how it is a gas evolution reaction because you're making a gas from 2 aqueous solutions. So we can see that it's in this table again, and that's the last example there. When you have the ammonium ion in a salt, you know, like NaCl, NH4Cl, NH4Cl, and you have a base added to it, so KOH here. In our example, it was KOH as well. So if you add a base to a salt of ammonium, you will make the ammonium hydroxide, right? The ammonium is from the ammonium salt, and then the hydroxide comes from the base. But this is unstable, and it dissociates or decomposes into the ammonia gas and water. So the other kind of gas evolution reactions that you need to be aware of are from the sulfite or bisulfite ions, which are SO3 negative 2 or HSO3 minus 1. When you combine them with any kind of acid, they will form the H2SO3 gas, which is the let me think. Okay, because this is a sulfite here. So we change the ending to -ous, and that's going to be the sulfurous acid here. And the sulfurous acid decomposes, it's also unstable, and it decomposes into water again and the sulfur dioxide. It's very similar to what the carbonic acid becomes, except you change the C by the S, and you see that it's very similar. And another type of reactant that will make gas evolution reactions are the sulfide. Sulfide, when they are mixed with any kind of acid, will make the H2S gas. So H2S is also a gas. So this document is a very important document that you want to have at hand when you are, working on chapter 7.